All right. Well, I guess we'll get started. It's 11 o'clock, 11:01 in fact. So this is the first in a series of Tuesday Tech Talks for this fall. So just to remind you, this is something we started up, this Tuesday Tech Talk bi-weekly seminar. We started this up in the spring as a test run, and it went pretty well. The theme in the spring was artificial intelligence. So we wanted to change it up in the fall and have something for the circuit-minded folks. So we're going to focus on electronic circuits and devices for this quarter. We got a great lineup of 5 speakers, top researchers in the world. And these are going to be bi-weekly. You can find a quick link if you go to the EECS webpage on the side. You can see the Tech Tuesday seminar series. Click on that and you'll get to this page here. So we are going to be recording this. So I guess watch what you say. That's just something we want to do so that we can put these recordings online and have people see them who can't attend at the regular times. But we're going to plan on always having them at 11 a.m. on Tuesdays, and we'll be sending out ads, the week before, so you can look for those and you can put it on your calendar. So without further ado. Today we have Tejasvi Anand, and he came to us from the University of Illinois. That's where he did his Ph.D. He got his Ph.D. in 2015. He did a short stint at IBM T.J. Watson Research before he came here, and then he joined us directly in the winter of 2016. And has been doing some really great work since then. So we're very lucky to have him talking to us today about some of his really interesting work on equalizer-free high-speed wireline communication. And he's been telling me about this for about a year, and it just seems really interesting. So let's let him tell us all about it. And I'll just say, if you have questions, put them in chat, or you can ask them at the end. We're going to have a question period, 15 minutes or so, and I'll be watching the chat, but you can feel free to ask them at the end as well. All right, take it away, Tejasvi.
Okay, thank you, Alan. Let's see, let me share my screen. Okay. Here it goes in the presentation mode. Okay. Well, good morning, everyone, or good evening, or wherever you are in the world. Welcome to my presentation. So before I begin, I'll just would like to acknowledge my past and present students who were instrumental in the work. They did all the heavy work, which I'm going to present to you now. I just made the presentation, and my funding agencies who were generous enough to fund my research. So in the next few slides, I'll give you some of the brief introduction of Wireline Link, where they stand right now and what are the problems. Starting with the links that exist today in the server area. And this slide on the left-hand side shows a server motherboards, and you can see the wireline communication links in the arrows. The red arrow shows the wireline communication that exists between processor to processor. And you can see that there are 4 processor slots, P1, P2, P3, P4. There is also communication links that exist between processor to the memory, that is the DRAM. Let me see if I can make it a pointer. And also from the processors to the other peripherals. So all these communication happens on wireline communication. And today, wireline communication is the backbone of the communication that exists today in the data center. If you take a look at some of the current standards of these wireline links, which is shown here in the table on the right-hand side, we see that these links are going all the way up to 100 Gbps, some of the recent or the upcoming standards. And another thing to note over here is that the speed with which the data rates are increasing. For example, I would like to draw your attention to the PCIe standard, which was in 2010 was 8 Gbps, but 2017 went to 16, 2019, 32, 2021, it's expected to come 64 Gbps. So it's like doubling the data rate every 2 years. And the thing that is fueling this high bandwidth demand or high data rate demand is really the artificial intelligence and the big data applications, which requires huge amount of data to go back and forth, memory to processor or processor to processor, or go inside the data centers as well. So this is just one slide summary of what a serial link is. So serial link or wireline communication consists of three parts. The first one is the transmitter, which consists of a multiplexer. The phase lock loop provides the clock, which can clock this multiplexer. The multiplex data goes to the output driver, and this output driver then pushes the data onto the channel. Channel forms the second part of this communication system. And typically, these channels are the copper channels or copper traces on the FR4 board, or one can also see cables, twisted cables, coaxial cables, etc. For example, in the automotive communication, as also the wireline channels. These channels are lossy in nature, and the graph below shows typical insertion loss profile of the channel. And one can see that the loss increases as the frequency increases. So you can imagine that these channels act like a low-pass filter. The third component of a wireline communication system is a receiver, and the receiver consists of mostly some front-end amplifiers, low-noise amplifiers, and then comes the equalizer. And I'll be spending a great deal of time explaining this thing. And then comes the slicer or a sampler, which is like a sense amplifier architecture, followed by some demultiplexer to get the data out. You can also see clock and data recovery circuits in this receiver, which is known as CDR, which is also supported by a phase lock loop in the receiver. Now this slide and the next few slides shows you some of the recent trends in the wireline communication systems. And with the help of these trends, I'll show you what is the problem that the wireline links face. And then I'll introduce you some of the known solutions and the work that we do here at OSU. So in this graph, some of the previously published work has been plotted here, which has been collected for the last 20 years. And this shows the data rate versus the year of publication. And this graph shows that the data rate continues to increase exponentially higher and higher up. And AI and big data applications are the key driving factors here. On the other hand, if you look at the energy efficiency of these links, where the energy efficiency is measured in energy per bit, that is how much energy we need to transmit one bit across the channel, versus the year of publication, then we note that the energy efficiency continues to improve, where energy per bit continues to decrease. It has been an exponential decrease. Please note that the y-axis is a log scale. Over the I would say, the first decade of the 21st century. But over the last few years, the energy efficiency improvement has slowed down and going towards saturation. And also note that all the papers are also sorted in terms of the technology nodes they are in. So you can also see that the efficiency has been improving as the technology nodes are scaling as well. So one of the reasons why the efficiency improvement has been slowing down or going towards saturation is the channel loss or the communication channel itself. And this slide shows the typical insertion loss profile of a backplane channel, where as the data rate increases, the loss that is offered by the channel at the Nyquist frequencies also increases. And what this means is that when you have a higher loss, then one see more intersymbol interference, and I'll be introducing ISI in more detail later on. And that basically results in using some form of signal processing in order to recover the corrupted data. And so the signal processing basically consumes some energy. So let's say, for instance, that one goes to a new process technology node and also pushes the data rate. But at the same time, the communication distances are not changing. We are not making our laptop smaller or our motherboard smaller, or the communication distances in the data centers are not changing. So the channel remains more or less fixed. As a result, at a higher data rate, one sees more insertion loss. And so even though we are using fine technology node, we end up spending a lot of energy in doing more signal processing in order to recover the corrupted data that the corruption happens due to the bandwidth limitation of the channel. So the net effect of using fine technology node doesn't give us a big improvement in energy efficiency. So there's only marginal improvement that happens with every node. So if this trend continues, where the data rates continues to double or increase exponentially over every 2 years, and on the other hand, if the energy efficiency seems to almost saturate out, then what we will foresee is that the power consumption of a wireline link will increase in future. And what this means is that, let's say if in a processor, if 20% of the total processing power goes to the I/O power, which is for the wireline communication, and the 80% goes to the compute, then in the future, if the trend continues, then this percentage of I/O power is going to increase. Now, please note that the total power we can burn in a processor is fixed, and this is due to the thermal constraints of the package. So if we try to burn more power, it will melt the processor. So that is fixed. So what it will do is that if the I/O power increases, it is going to push or put a constraint on the compute power, which is detrimental to some of the AI and big data application, which also needs a lot of computing. So this is one of the biggest concerns. So here is a different way to look at this problem of the communication channel. And in this slide, I'm plotting the energy per bit on the y-axis and the channel loss for all the published work on the x-axis. And we see that there is a trend line which exists. And this line, dotted red line, shows that the energy per bit goes up by 10 times for every 30 dB increase in the channel loss. And all the published work is above this particular line. It's very hard to break this trend line. The other point to note over here is that because this trend line exists, it is very hard to communicate on a channel loss which is beyond 50 dB. That's why we don't see published work which is communicating beyond 50 dB, because the energy per bit is just so much that it is not, I would say, impractical to be used in a commercial application. So what I call this particular portion is the bandwidth wall that exists in a wireline communication system. And what we need is basically to break this wall is to change this trend line where the energy per bit doesn't go up by 10x for every 30 dB increase in channel loss. It should be a more gentle increase in the energy per bit. And so what we need today is some new ideas or technologies which will help to break this wall, and that will help to continue to push the data rates further in the same channel while seeing bigger and bigger channel loss. So to explain the problem in this one slide of bandwidth limitation, shown on the left-hand side is the data which, let's say we want to transmit. Let's say we want to transmit 100, and the channel is bandwidth limited. So by the time we transmit this particular data and the data comes out of the channel, we see that a simple pulse that we transmit has spread out. So the sharp edges has become smooth, and the pulse has sort of interfered with the neighboring bits of zeros. And these blue interference, voltage interference that it has created, we call this as intersymbol interference, because it is the interference in the adjacent samples, adjacent symbols, sorry. And so on the receiver, if let's say we want to know whether we have got 1 or a 0, we put a slicer with a threshold with a dotted line. And then the output of this slicer will tell us, okay, we have got this one. But at the same time, we will also incorrectly slice the adjacent bits to V1 as well. So these are the bits in error. So these error bits are known as ISI errors. Uh, One thing to note over here is that the ISI error is deterministic in nature. And by meaning of deterministic is that if we know the channel loss and if we know what kind of data we are transmitting, then to a very large extent we know for sure that what kind of errors we are going to get. And because it is a deterministic quantity, we can also reverse the side effect or the effect of ISI in the communication system. So there are today's world 3 solution exist in order to reverse what the channel has done or to get an error-free communication on a bandwidth limited channel. And these solutions I have noted it down at different levels of a communication stack. The first and foremost, which I think most of you will be familiar with, is equalization. And the idea over here is that we try to put a high pass filter in order to compensate for the low pass nature of the channel, and the filters can be on transmitter and receiver or on both sides. Some of the unconventional approaches which my team has explored here at Oregon State is to go with the line coding and see if there are new line coding techniques which can do the similar job as what equalization is doing. And the third approach, which my team has explored, is to come up with new form of channel coding, which is all a back-end solution where we don't try to manipulate or put a filter onto the channel and just encode the data and do some form of simple error correction in order to recover the data and get error-free communication. And in this talk, I'll be spending quite a bit of time to introduce what this channel coding technology is that we are developing. And I'll touch upon a little bit on the line coding technique that we are exploring as well. So let me give you a 2-slide introduction of conventional approach, and then I'll move on to the channel coding approach. So in this slide shows what conventional equalization techniques that exist today, or I will call it a filtering technique that exists today. So there are 3 types of filters or equalizers we can put on a communication channel. The first one is the continuous time linear equalizer. So you can think of it as like a high pass filter. Typically it is on the receiver or front end of the receiver where this guy is placed. The second is called a feed forward equalizer. We call it FFE in short. And you can find this thing mostly on the transmitter end. You can think of FFE is like an FIR filter for those who are familiar with digital signal processing. And then we have what is known as a decision feedback equalizer or a DFE. And DFE is on the receiver side. And you can also think of DFE as like a non-linear IER filter, non-linear because there is a slicer that comes in the loop as well. So all these filters have their advantages and disadvantages. Advantages, they are simple. Disadvantages that they also amplify noise. There's also a very tight timing constraints that exist here. And also, so far, our innovation in the wireline communication industry with whatever data rates we have achieved is thanks to these filter technologies and the researchers who have innovated them over the last few years. But nonetheless, that now because of these filter technology, we are seeing that trend line, which is 10x increases in energy per bit for every 30 dB increase in channel loss. So here is what the filter does is if we have a transmitted data, it goes through a lossy channel, then what we see is a corrupted data. This is like an eye of a data. And if we try to sample this data in the middle, we don't know whether we are getting the right 1 or 0. On the other hand, if we have an equalizer, then the same data passes through the channel. And if you have an equalizer, then equalizer undoes what the channel low pass is doing. So it is high pass, and the effect is that you get a band passes type of function up to certain frequency, and then one gets an open eye, and then we know that we are either we are receiving 1 or a 0. So the key is that equalizers are all working to make sure that we get an open eye at the receiver. So this is something to remember in this talk now, And when I introduce you the error coding technique, this concept will be completely reversed. So to start with the channel coding technique, I would like to introduce you some of the prior art. Because whenever somebody talks about channel coding, the first thing that comes to mind is, well, these codes, Reed-Solomon codes, low density parity check codes, turbo codes, they exist for the past several decades, have been developed by mathematicians. They are like a block codes, and the way it works is that you have a block of data, and then you put some parity bits at the end of that block or in between that block, depending on the code. And then the receiver checks based on the parity bits to know whether the error has occurred in that block of data. And if one has more capability, add more parity bits, then one can also correct some of the errors. We can also have convolution coding, and then decoding technique can be maximum likelihood, Viterbi, which is a fancy form of maximum likelihood. One thing to note here is that all these data coding techniques that exist out there, they have been developed for a noise limited communication system. By meaning noise limited means they are SNR, they are designed where the communication system is SNR limited, because they have been developed mostly for the wireless communication system, because wireless communication has been SNR limited since its inception. On the other hand, wireline communication is a bandwidth limited system to start with, but in future it will become a SNR limited as well, but let's not go there for a while. So what I'm trying to say is that the technology or the codes that have been developed or that are out there for error correction has been mainly for SNR limited channels. So that's one problem, because they cannot handle the ISI errors. The ISI errors results in a bit error rate of 0.1, 0.2, and these error correcting codes require much more better BER in order to improve the BER further. The other problem is that they have a large error correction latency because of the lot of loops and the background processing that runs to several hundred nanoseconds, and that's detrimental to some of the processor to processor, or especially the applications which runs in the data centers. And the third is that they are very big, bulky. You can see it on a chip. On the chip micrograph, they stand out, and they are energy inefficient in nature. So we saw all these disadvantages, and then we thought, okay, why don't we create a new channel code, and then do some error correction ourselves, and that is specifically designed for ISI type of errors. And in order to do that, I would like to show you that what was the thought process behind coming up with that code, and then the error correction logic. So to start with, we looked at the ISI with a different perspective. So let me show you the same scenario again. So we have a bit of data that we want to transmit, and this bit actually spreads out. So if we try to sample this data, what we get is a bit and bit errors. But then one has to make more observations here. The first observation we would like to make over here is that the bit errors that it is coming is similar to the bit that has been transmitted, and the bit errors that are coming are identical in nature. That is, they are consecutive identical digits that have been created. So knowing these two observations, then one can think about a code where the consecutive identical digits does not exist at all. So for instance, if you have a data, we encode the data in such a way that CIDs, or consecutive identical digits, that is 1, 1, 1 or -1, -1, -1, doesn't exist. And if we pass that code through the channel, and if the channel does something where it creates these CIDs, then we know for sure that error has occurred due to ISI, and then we will have some ability to correct the error. So there can be many codes that can have a feature where CIDs don't exist. But the code that we selected for this ISI resilient channel coding is the die code. The reason we selected die code is because it is very simple in nature. Die code has been around for quite some time. It's not something that we have created. We have just used it to do error-free communication or to do forward error correction on a bandwidth limited channel. And the way die code is generated is if you have a sequence, we delete that sequence by 1 bit and we subtract the 2. And we get 3 voltage levels, 1, 0, -1. And note that in the die code sequence, one can never have consecutive 1s or consecutive -1. That is, we cannot have 1, 1, 1 or -1, -1, -1. Now one can argue that, oh, what about these consecutive zeros? They exist in a die code. Aren't these consecutive identical digits? Well, yes, CID 000s are CIDs, but we have to remember one thing about ISI. And the thing is that ISI will be created by a voltage transition on a channel which is above the average voltage or below the average voltage. So 000 is the average voltage of the channel. Anything above or below will create an ISI. So 1 and -1 creates ISI. Zeros, on the other hand, doesn't create ISI to a large extent. So we are saved for that matter. So here is how the error correction will happen. So if we have the data, we will do a die code encoding. So the data will look something like this. So this is a very simple example to show functionality. And then we transmit this data through the channel. The channel spreads out these bits. And the red ones are the bits which are the ISI that has been created. And then we sample this data at the receiver. Note that we have to use 2 threshold voltages, 2 dotted lines shown here and here because there are 2 I's, and 2 I's were created because there are 3 voltage levels, 1, 0, -1. So after sampling, we get bit in error, that is 1 was correct, red ones are the bits in error, -1 in error again. And then what we do is we use a very simple error correction logic, which is a simple truth table where we look at the 2 ones and we see that, okay, if the second one is coming with the first one, we force the second one to 0. And also we force the second -1 to be 0. And this way we will do the error correction for the data. Now this is a very simple example. There are many assumptions made in this particular example. This is just to show you the basic concept. Assumptions were, for example, it's only post-cluster dominant channel, etc. But we have also experimented with other channels with more complicated error correction logic, and this technique seems to work. We then fabricated this transceiver in a 65 nanometer CMOS process to see how the complete system is going to work. On the transmitter side, we have a PRBS generator. We have some parallel pre-coding to avoid error propagation. The data goes through multiplexers, it gets encoded, die code encoded, it gets to the channel. The receiver has a very simple front-end amplifier and then bunch of slicers, retimers. There are a couple of error correction logics. We want to experiment with different types of channels, and then a die code decoder. And note that there is no equalizer or any filter that we have placed in this particular communication link. So here is an example of transmitter. So what we do is that we take the data, we pre-code it. This is for avoiding error propagation. We then encode it with the die code encoding. So 1 minus Z inverse is the transfer function. So we have the data, we pre-code it, we encode it with the die code, we get 3 voltage levels. We pass it through the channel creates ISI, so this one spreads out. And here is the receiver. So the receiver consists of 2 slicers and this error correction logic, very simple error correction logic shown here, where it is a delay and an AND gate with a bubble in the beginning. And what this does is it creates a truth table, which is shown here. So the important point in the truth table is the last row, where if we have previously received one and then the current one has come, then what it will do is it will force the current one down to 0. And the die-code decoder is a simple OR gate. So extremely simple architecture, no feedback, no timing constraints, very low latency. So just feed forward and do forward error correction. So here was an example. So if we have a data D of n, we do a die code encoding. We pre-code it and do die code encoding, and then pass it through the channel. Then when we have this ISI, this creates a 1 in SH of n. The current bit is 1, and this gets forced to 0 in CH of n. And then when we do the OR of CH and CL, we get the original data, which is the data which we were transmitting. So this was just shows a very simple example and the very simple error correction logic that we have used. So apart from that error correction logic, we have used other error correction logics as well, which much more complicated truth table in order to take out precursor ISIs and precursor and post-cursor ISI dominant channels as well. And this shows the measured results, right? Shows the die micrograph, the test setup, and shown here at the transmitter output is an eye diagram, which is a near-end eye diagram. There are two eyes that we were transmitting because of 3 voltage levels. By the time it goes through the channel totally closes the eye. So what we sample by our samplers at the receiver is a total junk data because it's a total closed eye. But by the time we do this error correction, then this is an in situ eye diagram where we move the threshold voltages of the slicer and move the sampling position of the clock, and we can get a BER of 10 to the minus 12. And this was done at multiple data rates. This particular experiment was at 13.4 gig. We pushed the speeds up to 16 gig, only limited by the technology node of 65 nanometer. The channel losses in this experiment was 23.8 dB at Nyquist at 6.7 gigahertz. We have gone to almost like 24 dB to show we can get a BER better than 10 to the minus 12. So shown here is a comparison table with the prior art, and the thing that makes it apart is the decoding latency. So here is a work which tries the same ISI error correction with Viterbi decoding and 8V10B encoding. But at the same time, this was like a reduced set Viterbi decoding architecture, but the latency still exists, which is 150 UI compared to 5 UI, or the total latency, which includes resynchronization and forward error correction. And this was done at a much higher data rate. Note the technology remains the same. Data rates can be higher because there is no feedback architecture. The energy efficiency can also be 4 times better, 2.5 picojoule per bit compared to close to 10-ish or 11-ish picojoule per bit. And the channel loss is also a respectable number. And this was, if we try to compare this technology with some of the previously published ways of doing equalization using conventional filters such as FFE, CTLEs, or DFE, we can see that the energy per bit numbers are comparable and better for the similar type of channel loss profiles. So what this demonstrates is that now one can have a different way, or I should say a totally orthogonal way of communicating on a bandwidth limited channel, where all one has to do is to add some backend on the transmitter for encoding, backend on the receiver for forward error correction, and one can achieve a error-free communication on 25 dB. And we are now experimenting where the error correction can go above 28 dB as well. And what one can think of it that now, let's say if our conventional equalizers with a reasonable energy per bit can give us close to 30 dB channel loss with a reasonable energy per bit. And if we want to increase the channel loss by another 30 dB, then we need not shell out 10x more energy per bit. We can have an orthogonal approach, which is something like this forward error correction, where you can add up another 30 dB by a marginal increase in the energy per bit, because all that energy goes in some form of front end and back end error correction. The second technique which we have explored, I'll briefly go in 5 minutes, is the line coding technique. And this is I will say is another orthogonal approach than the conventional equalizers. So to introduce line coding, the first thing when one hears about line coding is Manchester encoding, because that's what comes to our mind. So in Manchester encoding, what happens if we have a zero, what we do is we send a zero followed by a one. And if we have a one to be transmitted, we send one followed by zero. And what Manchester encoding does is that it shapes the power spectral density of the data. So NRZ typically looks like a sinc function, but if you have a Manchester encoded data, then it shapes the power spectral density where the low frequency components are attenuated, the high frequency components are amplified. And this high pass shaping of the PSD is the main feature or the main reason why if you pass a Manchester encoded data on a wireline channel, which is a low pass, by the time the data goes to the receiver, one can see that the eye will still remain open because this high pass nature compensates the low pass nature of the channel. This is a very old technique. It was first introduced in 1949, but there are problems with Manchester encoding. And the problem is that if you have a consecutive bits like consecutive ones or consecutive zeros, then what Manchester encoding creates is these narrow pulses or narrow glitches in the data. Now, if one can imagine that if you want to do this Manchester encoding at a very high data rate, 56 gig, passing these narrow edges through the pre-drivers and drivers and then reliably putting it on the channel is a very big task and almost impossible if you are looking at, for example, 10% pulse width where one needs rise fall times less than a picosecond. So this is not possible even with the fine technology nodes. So that was the limitation, and what we explored here at Oregon State is to come up with a new line coding technique which removes all the limitations of the Manchester encoding and still use the useful feature where one can get an error-free or an open eye at the receiver by just doing line coding. And what we did is that, for example, if we have two CIDs that we want to transmit, so instead of transmitting the full CID or two CIDs, which creates ISI like this, we reduce the edge of those two CID bits based on the channel loss. And as a result of that, we could suppress the ISI which was created because we were transmitting those two CIDs. And we extended this to any number of CIDs. We can have n CIDs, and this is the ISI created by n CIDs. And we were able to suppress this ISI by just modulating this edge of these CIDs, again, proportional to the channel loss. And as a result, we could reduce the ISI created by these CIDs. And this is what we call it as integrated pulse width modulation, or IPWM line coding. And the idea is like this. For example, if you want to suppress a post-cursor ISI, then based on the CIDs, we move or modulate the edge based on some weight, let's say alpha 1. This is the trailing edge. And for all CIDs, we do it. For 3 ones, we modulated more. For 4 zeros, we modulated even more. And for if you want to do precursor ISI correction, then we modulate the leading edge, again with the different weight factors. And the advantage of doing this is note that in the modulated data of IPWM, there is no narrow pulses which were created in the modulated data. So this basically relaxes the constraints that the Manchester encoding creates, and one can transmit this data just like one transmit an NRZ data. There's no this is still a rail-to-rail signal, no voltage levels, no DACs, no voltage level DACs are needed. What we did is we created a phase DAC, which we could do it very accurately with the accuracy of less than a picosecond in 65 nanometer CMOS. So that was a very feasible way of doing it. So these were just simulations showing by modeling it the IPWM and FFE in the circuits, and we did a comparison to see how effective this new line coding technique is compared to the conventional equalizer, which is FFE. We transmit 16 gig of data, channel loss was like 19 dB at 8 gigahertz. The IPWM and FFE eye openings are compared, And we see that it is slightly less, but it's still a very close to it in a ballpark sense. And then here goes the Manchester eye that comes out when we see a channel loss of 19 dB. Again, the horizontal eyes were comparable, vertical eyes even slightly better than the Manchester encoding. So this shows the line IPWM line coding is at par as far as the performance is concerned with the conventional FFE or the Manchester encoding. And note that this is orthogonal to what FFE does. FFE modulates the voltage, IPWM is modulating the time edge. So we demonstrated this technique in 2017 at ICCC, and we demonstrated by a transceiver where the transmitter has this IPWM modulation, and the receiver has a CTLE in order to show that this line coding can work with a conventional equalizer as well. So in the next two slides, I'll show you the how the eye diagrams are looking. So we experimented with 3 channels, 14 dB loss, 19 dB loss, 23 dB loss, and the eyes were closed when no line coding was used. On the other hand, if we enable IPWM line coding, we could see that the eyes open up. Depending on the channel loss, the eye openings were different, but the eye was open enough that we could put a slicer, a regular slicer at the receiver, and we could sample the data and get a BER of 10 power minus, better than 10 power minus 12. So because of the CTLE, so this IPWM alone can push it to 23 CTLE. With the help of CTLE, we could do a 27 dB channel loss, which was demonstrated in that conference. So in conclusion, I would like to say that bandwidth limitation is one of the biggest concerns that the wireline communication is facing. And innovation at the circuit level alone, or innovation at the low end of the communication stack alone, have started to give us diminishing returns. And therefore, I think that we need to look up communication stack. We need to look vertically up in the communication stack and start to innovate at different layers of the stack if we want to get a breakthrough in the energy per bit, and basically if you want to, what I call it as, break the bandwidth wall, we really need to innovate higher up in this stack. So with that, I would like to thank you all for your time and for joining me here in this presentation, and I'll be happy to take your questions and comments.
All right, well, thank you. I'll clap for you anyway. Yeah. So that was great. Well, we can stick around for questions. You know, anybody can turn off their mute and ask a question or put it in chat. I do have a question, unless somebody else does.
I had a question. Have you explored combining maybe partial equalization with the other techniques to look at what a hybrid approach would do?
Oh yes, that's a good question. So right now, one of my students is working in that particular project. So we are trying to see, we are trying to combine FFEs and CTLEs with the channel coding technique to see how orthogonal and how much channel loss we could take out using that. So it is a work in progress. We have got the chips out. The testing has been slow, but we are now testing that particular approach.
Thanks.
Any other questions? I'll go ahead and ask mine. So, yeah, I thought it was interesting that your work seems to open up some doors between information theory and channel coding and you know, wireline communications that may not have been opened. So you were mentioning that the assumptions of traditional information theory sort of are not consistent with, you know, the types of errors that you see in wirelines, the bandwidth limitation. Has there been a community studying that type of error? It's just a very small community, and if not, do you see any people getting interested in this in that community?
Yeah, that's a good question. In fact, so we have a very great professor here at OSU, Belabos, and I work closely with him, who works on this information theory and channel coding. So there has been a niche study in this area for bandwidth limited channel, but it has not been, I would say, fully explored and experimented out in a wireline communication link. And one of the reasons why those things were not done, because there is a big disconnect between the theoreticians and the circuit designers. Circuit designers never talked to the information theory people in order to discuss their problems for those guys to come up with a solution. So that has been the biggest problem so far, because the problems of the circuit designers were solved by these equalizers. So they were sufficient in order to solve the problems. But now they are becoming not so sufficient. So now is the time when the circuit designers are talking to these channel coding guys and trying to question the assumptions of some of these standards that are out there, and see if there is a way to push the envelope further. So I would say theory was existing in a very niche area, but never explored or never got full attention up till now.
Yeah, thanks. Seems like a lot of low-hanging fruit on both sides. Hopefully. Any other questions?
Okay, yeah, I have one question. Thank you for your nice presentation. Can you go to the page 23?
Page 23. Okay.
Yeah, I have two questions here. First, after the channel loss at the signal at the RS input, seems the signal amplitude is quite small.
Yes.
Yeah, how do you determine the threshold? If the signal is smaller, it's very, I think, noise sensitive.
Yes, the signal amplitude nevertheless got small, and definitely a noise also plays a key role. So what we did was we were modeling this particular behavior in our simulations when we were designing it. Because of that, we deliberately put these two amplifiers in order to bump up the signal amplitude, so that the offsets in the slicers don't create problem for us when we are trying to sample the data. The question about finding the right point for slicing it is I would say there is some mathematical theory that we have come up. We have shared some of that information in our GSSE journal paper, and the information of that is in my website. It was published in, I think, June or July 2020. So there is a technical way we can come up with which we can determine what these threshold voltages are in order to get a very good BER. To summarize, I will say they depend on the channel response profile. So it requires some form of tuning or learning in the beginning when we were testing this. So we were sweeping it to find the right location of these thresholds in order to get a low BER.
Okay, thank you. So I understand. So definitely we need I think the amplifier is needed as the first stage, right? Amplify signal.
Yes, amplifier will be the low noise amplifier has to be there in order to get those voltage levels safe enough for the threshold, for the offsets of comparators not affecting, or kickbacks should not affect the signal.
Okay. The next question is how the clock recovery works.
Oh, that's another important thing. So we have been thinking about it, but I will be honest that I didn't find too much bandwidth in solving that problem for now. But it is on our list because putting a clock data recovery with such kind of a slicer and such kind of error correction logic will be of importance. So I will say I don't have a correct answer for you or a good answer for you right now, but it will be a good area of research going forward.
Okay, thank you.
Yeah, I have a question. Hello.
Yes, please.
Yeah, I think it's a very interesting topic, and it's great talk. I just wondering, in the case of a different cable lengths or different board trace lengths, is this coding approach you're going to change, or you're going to do some kind of adaptation or learning first, and to decide, what kind of coding, how many bits you're going to do the pre-emphasize or precursor or after cursor emphasize, or whatever those approach you use. Is that length dependent?
No, that's another good question. So you are right that different board lengths, actually different board lengths will require different form of error correction is what I will say. And this is what we have observed. Different channel losses were requiring different types of error correction logic. So our encoding remains same. And that's actually I will say, the biggest benefit, or one of the strongest force in such kind of technique is that we fix what is coming out from the transmitter, and we will only adapt our error correction logic on the receiver. So there is no back channel information that we need to send to the transmitter to do any form of adaptation on that end. Based on our initial experiments that we have done, we have seen, for example, in this particular error correction logic, we were looking at 2 consecutive bits at the same time. We have experimented with 3 consecutive bits, 4 consecutive bits, 5 consecutive bits. 6 consecutive bits was difficult to create a truth table. But nevertheless, the sequence is that the more parallel bits you look at in order to make a decision, higher channel loss can be taken out. And depending on what decision we make at the output of truth table, various types of channels, whether it's a precursor, post-cursor, maybe the channel is not good, little reflective, and so on, those can be corrected to a certain extent. So those were like some basics experimental simulation studies we have done. So it will require, in short, some form of learning and tuning the error correction logic for every type of channel.
Okay, so you probably like suggest the customer when they use this technology, technical, they're going to do some kind of pre-learning or on the board, or every board they have to do some kind of learning, or this kind of, let's say, one kind of layout, it should be, in general, it should be, one learning should be enough, or one structure.
Okay, so to answer that, I will put it in 2 scenarios. The first scenario is, for example, if the loss is not so significant. For example, if we are looking at 30 dB loss, and if let's say that it is a part of a standard, because when something becomes part of standard, many things gets I would say streamed out in a way that many things are known in advance, sometimes about the type of channels as well, or limitations, or I should put limits on those channels. And so when it comes to that, then one can have fixed truth tables where we are not pushing the envelope on the loss. And so there must be, to a certain extent, there will be no learning required. But on the other hand, if we are pushing the envelope, we are pushing to a very high loss. In those cases, I think some form of learning will help to get a BR better than 10 ⁻12.
I see. Well, thanks. Thank you very much.
You're welcome.
Well, thanks. I'm sure if there are more questions, you can ask Tejasvi through email or however else you can contact him. But yeah, thanks everybody for coming today. It was great turnout for our first talk, and hopefully we can keep it up. So have this on your calendar, and we'll see you next time.